Alright, let's get into some chemistry. So, basics of chemistry. So first, what the heck an element is, right? An element. Weird definition, we talked about how essentially you need certain definitions in chemistry to define each other. They're essentially mutually exclusive, right? So an element is just a pure chemical substance comprised of the same types of atoms. Now, what in the world, is an atom? Is a chemical structure whose parts of which define an element, right? So, kind of weird to define these guys, but it makes a little more sense when you start to draw some of them, right? If you look at something like a hydrogen atom, we just have a hydrogen atom. We know it has a nucleus in the center. Of course, you can analogize this to a cell, right? It's very similar in structure, which I always find these kinds of things really neat. We have this nucleus in the very center. We have positively charged proton, and then we have a neutron, right? And then surrounding that, we have this negatively charged electron floating around the outside. So an element is essentially this chemical substance comprised of a specific number of atoms, right? And it's the features of which, at least in an oversimplified manner, are defined by their atomic number or the number of protons. So in other words, the number of protons are what gives a specific chemical element its attributes, right? At least at this level. So, in any case, we have this nucleus, positively charged protons, and then we have these neutrons in the center with it, which provide mass but provide no additional charge. And then around that we have these electron shells and essentially these negatively charged particles that float around the outside. Now, protons and neutrons, they're actually made up of quarks. I don't know if you guys remembered this, but we talked about this when we briefly discussed quantum mechanics, quantum physics, and essentially that's just getting a little bit smaller with these things, right? You can't get much smaller than electrons, but protons and neutrons are actually made up of quarks, and this isn't really overly important to biology, but it's just a neat thing to know because you hear that word on television a lot, and most people have no idea what that means. But essentially, just know that you can break protons and neutrons up into quarks. You have these other really important elementary particles, things like neutrinos that we'll never talk about, but that float around the universe. Photons, which we will talk about later in the semester because they're what essentially power photosynthesis. And then electrons. But in any case, protons and neutrons are made up of quarks. Now, atomic number is the number of protons, right? Number of protons is the atomic number. Over here for a little bit. Atomic number. And protons plus neutrons. That's the atomic mass. Now, as I mentioned before, the number of protons are essentially what define the characteristics of any particular element. Electrons are important because they're what's involved in bonding, and neutrons just help add mass to that element and are actually involved in different versions of the same elements. Because I think one thing we kind of grow up learning when we learn about basics of chemistry, if we ever even get any of that education, is that essentially, well, you have hydrogen, right? But that's actually not really the way it works. You have isotopes, which have a different number of neutrons, and essentially some of them have really neat characteristics, some of them are radioactive. But in other words, you have different versions of the same element floating around the atmosphere, right? We mentioned the fact that carbon-12 is the most popularly or the most frequently found version of carbon, but there are other forms of carbon, and those are carbon-12, carbon-13, but these are called isotopes, right? Isotopes. This is when you have different number of neutrons. Now, those isotopes are constantly trying to become the most stable form of themselves, right? And carbon-14 is essentially always trying to become carbon-12 because carbon-12 has 6 protons and 6 neutrons and 6 electrons. It's essentially neutral. We can just anthropomorphize it and just essentially say it's the most stable, it's the happiest, right? Because it has all the same number of elementary particles. But the process by which isotopes do that is through the act of radiation, right? We talked about half-life how long it takes any given amount of radioactive isotope to stabilize, right? And certain elements have certain half-lives, and we can actually measure the ratios of one isotope to another and really old stuff, really old things, and carbon date it, right? That's what carbon dating is. But we also talked about how radioactive isotopes that are constantly trying to shed those elementary particles, right? They're trying to get rid of their neutrons. They're trying to become a different isotope or the most stable isotope. Sometimes they mess up, right? Sometimes they get rid of protons, they become a different element. And sometimes they get rid of their electrons, and that changes their charge, and they become ions, right? Ions are just charged particles. And that's when they have more or less more negative or positive charge, right? More negative or positive charge. We talked about sodium as a really common example of that, right? Sodium and chloride are really common examples of charged particles that also form salt via ionic bonding, right? But this is essentially just a basic overview of the different characteristics that we find in elements. When we talked about radiation, we talked about how essentially getting rid of these particles can cause damage to cells, right? That's how we form free radicals. That's also how we can form cancer. We talked about the Bikini Atoll. We also talked about Fukushima and how it's leaking radioactive cesium into the ocean. But overall, you just need to know the really, really basic information about these things, right? All the things that we're talking about right here, okay? So ions are these charged particles where we have either a greater number of protons in the nucleus, then we have negative electrons surrounding it, or we have a greater number of negative charges surrounding the nucleus, making it a negatively charged particle. And in that way, we can actually form bonds, right? So you guys know basics of how opposites attract. So when we have things like sodium and chloride, we have these charged particles, right? It's just because, without drawing out the full or complete electron shell diagram, ions or ionic bonds occur when we have a nearly full empty outer electron shell that approaches it nearly. We have a nearly empty outermost electron shell that approaches or comes in close contact with a nearly full outermost electron shell. So, if you can remember, essentially, without drawing the full entire combination of sodium chloride or table salt, chloride essentially has one electron vacancy. It's one empty spot. Going all the way back to your basic rules of bonding, right, where most elements want to have 2 electrons on their innermost shell and 8 on every shell after that, right? Just these basics are things you should already know. We have this electron essentially being transferred to this chlorine, which now has more negative charges, more negatively charged electrons on its outermost shell than it does positively charged protons on an innermost shell. And then sodium becomes positively charged because of the opposite relationship, right? There's more positively charged protons. And in that way, we form these things that we call ionic bonds. And this is how we get table salt, right? Just a really basic example using a really basic term in chemistry, ions, that can lead and form ionic bonds. Now, talking a little more about bonding, right? Ionic bonds are not the only type of bond among chemical elements. In fact, not anywhere near the most frequently found. You also have bonds that are covalent. And covalent bonds involve the sharing of electrons. Right? So, covalent bonds occur between elements that both need electrons to be as stable as possible, right? So if we have 2 hydrogen atoms close to each other, what they'll do is they'll overlap their electron shells. Each one of them has 1 electron, and these electrons essentially will transfer between both of these atoms, and in that way each of them has the most stable number of electrons that an element can have on their innermost shell. There's only 1 shell in hydrogen, and that's 2, right? So each of these has 2 electrons circulating or rotating around the nuclei of both of these hydrogen atoms, and here we're looking at hydrogen gas, right? Now, this is a very specific type of covalent bond. It's called nonpolar because we have this equal sharing, right? Now, if there can be equal sharing, there can also be unequal sharing, where you have different elements essentially hanging out with those electrons for a longer period of time, right? Now, hydrogen is probably the most simple example. We also talked about methane. We can just draw the Lewis structure for methane. And you can just get the idea without drawing this complex electron shell diagram. This is a symmetrical molecule, right? And because of that, there's this equal sharing of electrons going around, right? There's an equal pull this way, equal pull this way. In any case, when you're equally sharing electrons, it's called a nonpolar covalent bond. Methane, we talked about how we can collect methane from the bottom of ponds to make essentially a nature-made flamethrower. That's neither here nor there. So when we look at unequal sharing of electrons, we look at something like a water molecule, right? And without drawing the overly complex electron shell diagram, remember, if you want to do this, you can draw 2 on the innermost shell. Then you could draw the others on the outermost shell, right? You can draw this. Man, I'm awful at drawing, but you get the idea. You can draw the electron shell diagram for water, right? We have oxygen, we have 2 hydrogens. Much easier than that is the Lewis structure for water, right? But either way, there's this sharing of these electrons. The difference is that oxygen is much bigger and much stronger. And think about this in terms of the fact that there's much more positive charge in the center of this nucleus right here in this oxygen atom. So the electrons that are rotating around spend much more time around oxygen because there's a positive charge attracting these negatively charged electrons. And that is why we have a disparity in charge. In fact, these oxygen, or the oxygen side of the water molecule, becomes a little negatively charged because of this phenomenon. And the hydrogens become a little positively charged because of this phenomenon, because these electrons are rotating around this oxygen atom for a continual period of time. And this is why we get hydrogen bonds. So hydrogen bonds are attractions between the positively charged hydrogens of one molecule of water and the negatively charged oxygens of another water molecule, right? So here's a hydrogen bond. So before you can have a hydrogen bond, you have to have this nonpolar covalent bond that actually occurs within the molecule first. So we have this unequal sharing of electrons that can lead to these hydrogen bonds, all right? And because of that, we have a lot of really unique characteristics of water that we'll talk about next.